Hello viewers, welcome back. In this video lecture, we are going to discuss the synthesis of phenanthrene and its some important reactions. Here, if you look the structure of phenanthrene, it is closely resembles to the anthracene. Only the one difference. You see, both contains 3 benzene rings, but you see that the fusing pattern in the anthracene, all the 3 benzene rings are fused in the linear form, and the phenanthrene it is fused in the angular form. That is the main difference. Okay. Now let's move into the isomers. How we can rotate the pi bonds to get the different isomers. Now you see here, so we can get 5 isomers by rotating the continuous pi bonds. You see, I am rotating here like this, like this. So this is the first form. So after rotation, so we get this the second form. You see, wherever it is the shifted, that I put this here. Now I am going to rotate further. You see, like this, like this, like this. So I get this third form. Now I am going to rotate further like this, like this, like this. So I get this fourth form. So if you rotate one more time by this way, so we can get total 5 resonant forms for the phenanthrene. Okay. Now next we move into the synthesis of phenanthrene. Already we learned the Haworth synthesis in naphthalene and anthracene. By the same way, but here we took the starting material is naphthalene and the succinic anhydride. You know that we also learned in the naphthalene there are 2 unique positions, 1 and 2. So mainly it will substitute at first position. You see, here the Friedel-Crafts acylation takes place and it is substituting at the first position. We are getting this intermediate, and followed by this Clemmensen reduction, this carbonyl group getting reduced to CH2, and this is getting cyclized by using the polyphosphoric acid by dehydration mechanism. So we get this intermediate. Again one more Clemmensen reduction. So this getting the C double bond is getting converted to this CH2. So here dehydrogenation, that is gives aromatization with the help of selenium powder. So we get the phenanthrene. So this is the Haworth synthesis as we discussed in the naphthalene and anthracene. The same way, same mechanism. Next, the Pschorr synthesis. Here the starting materials are this 2-nitro benzaldehyde and this is the phenyl acetic acid. If you could have studied the Perkin reaction the same way, the Perkin reaction principle is applied here. You see here, this is the phenyl acetic acid, the CH2 is in active methylene group. In the presence of sodium acetate, it acts as a base, it forms a enolate ion, and that enolate ion will attack this carbonyl carbon of this aldehyde, followed by dehydration. So we get this product. Okay. After that, this nitro group is reduced in the presence of iron powder HCl. So we will get this nitro to amine, and followed by a diazotization reaction. So I taught you already how to do the diazotization reaction, condition and the reaction mechanism. So if you want to learn more about the diazotization reactions, please go through the description link which I given. Okay. Then it forms the CC linkage in the presence of copper powder. So it is connected, followed by decarboxylation. So there is a removal of carbon dioxide to get the phenanthrene ring. Now one more method from benzyl. So you know this, how the benzyl can be prepared from, there are so many methods to prepare benzyl. So if you take the benzyl and heat with aluminum chloride, So it gets cyclized, it forms phenanthrene 9,10 dione and followed by the reduction, and so we will get this to phenanthrene. Now one more method is Bardhan Sengupta method. So you take this phenyl ethyl bromide, so reacting with magnesium to convert this one to Grignard reagent. So we know that the Grignard reagent and this carbonyl compound, so it will undergo nucleophilic addition, so we will get this kind of alcohol product. So the dehydration of this alcohol, this is a tertiary alcohol, so we will get this intermediate, and this intermediate is cyclized to get this skeleton. The 3 cycle contains a skeleton and followed by dehydrogenation, so we get this phenanthrene. That important point in this reaction we should understand is, so listen carefully. So when the dehydration reaction, so it will get protonated and forms this elimination reaction, so we will get this carbocation followed by stabilization. So either this hydrogen may get deprotonate to give this product, and here there is an hydrogen and this product is possible. But you see here we will get always the endocyclic double bond, not the exocyclic double bond. Here the endocyclic double bond is most or more stable than the exocyclic double bond. That's why this intermediate is more preferentially getting formed. Okay, this is the key step we should understand it. Okay, so this all about the Bardhan Sengupta method. Next we are going to see the reactions of phenanthrene. As we know that, so these are aromatic compounds, so it will undergo aromatic electrophilic substitution reaction. Now if you see this phenanthrene, there are 5 unique positions, you see, that I labeled here A, B, C, D, E. You see there are 5 unique positions. So among these 5 unique positions, mostly the phenanthrene, that aromatic electrophilic substitution favorably occurs at 9th position, because you see, if this electrophile is getting attacked or substituted at this 9th position, you see, it forms this kind of carbocation. At the time, you see here both the 2 phenyl rings, the aromaticity is intact, so it is not get disturbed, so it remain intact, that aromaticity. So that's the reason, so it always favors the 9th position. So you can draw various resonance structures and also you try for the various positions 1, 2, 3, 4. Okay, that you will get these various resonance structures. Now we are going to see some individual aromatic electrophilic substitution reactions. For example, as we discussed in the anthracene, see, this is a nitration, so you preferably use acetyl nitrate, as I told you in the anthracene, because if you use the arch condition, so it will oxidize this, the 9, 10 position. This also very vulnerable, okay, more sensitive. So we have to use the mild nitrating agent, that is acetyl nitrate. So we will get like this. So this is a 9-nitrophenanthrene. Now the sulfonation. Here we use the sulfonation generally by the mixture sulfur trioxide and H2SO4. Here you see, mainly here we are getting mixtures of this sulfonic acid. You see here the sulfonic acid substituted at 2nd position and 3rd position and 9th position. Please remember that it is a temperature dependent, always that 9th position favored by that lower temperature. Okay, 9th position, and the 2nd and 3rd by higher. Okay, 2nd and 3rd always favored by high temperature. Okay, so these are about the sulfonation reaction. Next we move into that another type of reactions, that halogenation. The same way as we discussed in the anthracene, if you use the chlorine, it will undergo addition reaction. Here both the chlorine get added into the 9 and 10th position. So it gives 9,10 dichloro, 9,10 dihydrophenanthrene. If you heat it in the presence of like alkaline condition, so it will give elimination product, so elimination reaction, so and forms the 9-chloro-phenanthrene. But if you use the Lewis acid like this FeCl3, that is a Lewis acid, the mechanism will go by aromatic electrophilic substitution. This is by electrophilic substitution product it will form by that mechanism. In the case if you don't use this any Lewis acid, it will give the addition mechanism, but here the substitution mechanism. That is the main difference. Okay. Now we are going to see the Friedel-Crafts acylation. Here, as we discussed in the naphthalene, if you change the solvent, we will get the selectivity. Here, you see, when we are using the dichloromethane as a solvent, dichloromethane is like this, CH2Cl2. Okay, this is the dichloromethane structure solvent. It acts as a solvent. Okay, dichloromethane. So when we use dichloromethane, this acetyl group is always substituted at 9th position. But if you use this nitrobenzene as a solvent, it will give at the 3rd position. So this is the main difference here. The solvent decides the positions. Okay. Next, reduction. So as you know that here the 9th, 10th, the double bond between 9 and 10th position behaves like an alkene. It can be easily reduced by hydrogenation. So it gives 9,10 dihydrophenanthrene. Now oxidation. So if you do the oxidation with the chromic oxide, so first it forms phenanthrene 9,10 dione, and followed further oxidation, it gives diphenic acid. Here it cleaves this between these two carbonyl bonds and forms this carboxylic acid at both phenyl rings. The product name is called diphenic acid. And this also highly vulnerable for the ozonolysis, because here the 9/10, the double bond between 9 and 10th position behaves like a alkene. So it can easily get ozonolized and forms this aldehyde that is called diphenaldehyde. I hope you understand this phenanthrene synthesis and the reactions. So thank you very much. So we will see in the next lecture. See you. Bye.